In the last video, we talked about breadth-first search, which provided an algorithm to find the shortest path from some source node to every other node in the network, assuming that all edges were equally weighted. And so we need now a different interpretation of shortest path when we talk about networks with weights. And so that interpretation is not just going to be the number of edges, but it's actually going to be the sum of the weights of all the edges along the path from one node to another. And so this is a simple example of one where this path has a larger number of edges, but this has a heavier weight. And so in this case, this has weight 10, but only one edge. And this has a weight 4 and only 4 edges. Maybe a context here, you could imagine this being a road network and trying to move from some source node to some target node. And so you're living in a world that every road is taxed or tolled a little bit. And in this case, you could take the slow way, which means that you're going to go along these 4 different segments, and each one costs you $1. Or you can go along this single segment and it costs you $10. So if you're trying to find the cheapest route, and so in this case, the shortest path represents the cheapest route, you would pick these 4 segments. Even though there are 4 roads, you'd rather have that direction since you're looking for the cheapest route. And so the method is called Dijkstra. If you can remember that spelling, you're ahead of me. And so it works very similar to breadth-first search with a small twist. And the twist is that when we assign a node its distance up here in this upper array, it is not necessarily a certain distance. So we may find another route that is actually shorter. And so these form upper bounds, or these represent upper bounds on the shortest distance from a source node to this given node. And so what we're going to do is there's going to be a crucial step, and this is the crucial observation that makes Dijkstra work, which is if we find the vertex or the node that has the smallest estimated distance, this is the one that we mark as certain. And then we denote that one as fixed and that it can't get any shorter, and that then we update everything else from there. Otherwise, the method works quite similar to what we had before. So in this case, we start at node 0. That's the node, this is S. And so we mark then the distance to be 0. Since 0 is the only node that's in this upper array, it is also the shortest distance, and so we now mark that as a known distance. So it is fixed, and now we look at updating the queue and then the distance array based on the neighbors of all of the known distance nodes. So now we look at the distance of all the neighbors from node 0. So node 1 has a distance of 5, and to node 3 has a distance of 6. And so we put these estimated distances up here in the upper array. We look at all of the estimated distances, and we determine that 5 is the smallest one, and so that is the one that we mark as certain. That connects to node 1, and so for that reason we put node 1 down here in the queue. And now we can process all of the estimated distances, not only from node 0, which we have a known distance to, but also from node 1. So if we add the known distances or estimated distances from node 1 as well as node 0, now we have node 0 connecting to node 3 with that same distance 6. Now node 1 connects to 2, 4, and 3. With distance 2, 3, and 4. And so we add the existing distance 5 to node 1, and then each additional distance. Notice in this last case, node 3, node 1 does point to node 3, and its distance is a total of 9. But since this is already bigger than the distance here to 3, that we will never actually end up using that, and that's why I've crossed that out. Of all of these distances, 6 indicated here, which we already had and we haven't changed. Node 2 has an estimated distance of 7, and node 4 has an estimated distance of 8. Out of those, node 6 is the smallest right here, and so we give it that check mark, which means that we now decide that is a fixed distance. It's a known distance. And so now we place that node 3, down in this queue, and now it is now the base from which we can spread. And so now we're going to be looking at all of the neighbors of 0, 1, and node 3. Node 0, we've already exhausted both of its neighbors, so now we'll just be looking at nodes 1 and 3 and their neighbors. So now we still have these node connections from node 1, but now we're going to add on the connections out from node 3 to its neighbors. So 3 connects to 4 and 6. It does also connect to 1, but since we already know that the distance to 1, we don't consider that. And so we're adding in this edge and this edge, and so that gives me to 4, it's 6 plus 4. So we already have a distance 6 to node 3 and then 4 to get to node 4. And then 6 plus 5. Notice again that 3 to 4, this edge here, this distance provides a total distance of 10, which is bigger than the distance using 1, which is 7. And so we're never going to use this distance. And so that's why I've crossed that out. The edge that we use from 3 to get to 6 has a total distance of 11, and so that's why we're going to place 11 up into the estimated distances. So of the unknown estimated distances, 7, 8, and 11, it's 7 that's the smallest, which is why we give it then the check mark here, and we place node 2 now down in our known distances. And so now we can again use this as our base to spread from. So now we're looking at also the neighbors of node 2, and so the only node that node 2 adds is node 5. That's a total distance of 7, which is the known distance to node 2, plus that 5. And so we can add this distance 12 into the spot for node 5. And so out of the ones that we don't know, 8, 12, and 11, 8 is the smallest for node 4, and so that is the one that we give the check mark, which means that it's certain. Then that means that we put node 4 down here in this queue, and we look at its neighbors. If we expand from node 4, then we get several other nodes. We already have node 5 and node 3, so we just add we even have node 6, so we do take a look at that just to see, but that edge is actually larger than this edge, and so then again we will never use this edge. The distance to nodes 7 and 8 is 8 plus 3 and 8 plus 4. That means that we can put those values up here in this array to fill this out, and we identify out of the ones that we don't know the distances. The estimated distances are 10, 11, 11, and 12. And so 10 gets the certain check. And so that is what we now put as node 5 down in this array as a known distance. Notice if you look at the previous slide, our previous estimate using this path, essentially from 0 to 1, 1 to 2, and 2 to 5, would have been a distance of 12. And it was only because we can now use node 4 that we got a distance of 5 plus 3 plus 2, which is 10. And so this is an example of where this estimated distance reduced after we added a node into our queue. Namely, 4 was what allowed us to get a smaller distance. Now that 5 is in the queue, now we can take a look at all of 5's neighbors. So that includes essentially just 8. So we can add the edge 5 to 8, which gives us 10 plus 2. Notice this is the same distance as using 4 to 8, which is also 12. But out of all the ones that we have, we have a distance of 11 and also 11. And so here you get a choice. I just pick the first one in the queue. This doesn't matter, but the first one in the queue is node 6, and so that's the one that then we put down here. We mark that as certain and put that down in this queue. Now we can look at all the nodes that are connected to node 6. That includes 7, which gives us a distance of 13. That's 11 plus this 2. So that's bigger than what we have using 8 plus 3, and so we'll never use this. The other neighbor is node 9, which we don't have an estimate for. That estimate is 15, and so we place that estimate up here. Out of the 3 that we have estimates for, 11 is the smallest, which is for node 7, and we give that the certain check mark, which means that we know that, and we put 7 down into this array here. Notice that these are kind of building up in kind of numerical order. That's not always the case. That's just simply how this example was architected. We could have changed the names of these nodes and it wouldn't have proceeded in numerical order. Now that node 7 is certain, we can add the neighbors of node 7, which include 10 and also 8. 8 is another example where it's a distance that's longer than the other paths that we have available to us, so we'll never use that. The distance to node 10, the first estimate that we have on that is 17, and so we put that up here into this estimated distance. Out of the distances that we have estimates for, 12, 15, and 17, 12 is the smallest. We can actually, like we noticed before, we can actually get there 2 different ways, along 4 or along 5. You could pick either one. It doesn't matter. Oftentimes we just essentially pick the first index. So we'll go from 4 using that edge to get to 8. And so we mark node 8 as a known distance of 12, and we put 8 down in the array. Now that we've marked 8 for sure, we can add its neighbors. So the neighbors of node 8 include node 10 and node 11. This is the first time we've had a distance, estimated distance to node 11, which is 15, and so we place that in this upper queue. Here's an example again of where we had a distance before of 17 to node 10, and now we have a distance of 16 using node 8 instead of node 7. So if we went through node 7 to get to 10, it would take 17, a weight of 17. But going through node 8, we can actually shorten that by 1, and so that's now 16. And so this number here was replaced. It was 17, and now it's 16. We've got 15 as an estimated distance, 16 as an estimated distance, and also this node here, node 9, also has an estimated distance of 15. And so we're going to mark 9 as certain and put 9 down here in the queue. We can now take a look at distances using node 9, but they are all longer, and so we're really just going to now take the best distance here to node 11, which is 15. We give that the certain distance and put 11 down into the queue. Then we only have one more node left. Now the only one remaining is node 10. We give that the remaining certification that that's the shortest distance and put node 10 down into this queue. And this completes the Dijkstra algorithm for this example. We said that the crucial observation to make Dijkstra work was the fact that out of all of the estimated upper bounds on distances, the smallest one was indeed final, and it was certain. And so we can kind of demonstrate why this is. If we think about this circle as representing the boundary between known distances and estimated distances, so anything inside is something we claim that we know the distance to, the shortest distance to, and anything outside is something that we claim that we have only an estimated distance. And so if we have a node V that's sitting out outside of this known distances, that if it has the shortest distance as any of the neighbors of all the nodes, so if there's another node in here and there's a connection out to another node, that this distance all the way here is shorter, this distance here is shorter than the distance from S to V, and all other neighbors of known distance nodes, then it has to be the one that has a certain distance. And so if it wasn't actually the shortest path from S to V, then that means there had to have been some other path. And that some other path would have to have some portion that would be inside the known distance part of the network, and then it would have some part that is out. And the fact that this has to use another neighbor of our known distances, so x we know the distance to, it's certain, y is an estimated distance, and so if this path from S to X, X to Y, and Y all the way to this V node is actually shorter than S to V, then that means that actually the distance from S to Y is shorter than S to V. And so that's a contradiction. And so that's why if S to V is actually the shortest, then it has to be a certain, and it has to be the only shortest way to get there. It's not, there's not a shorter way that could take another path using a different neighbor node to get there. It's worth talking just a little bit about the computational complexity. Similar to breadth first search, we have to look at all the neighbors of nodes. So again, we're going to use the approximation that this is m over n, the average degree of the network. And so we have to repeat this, but we also have to make sure that we take a look and check to see what is the smallest estimated distance. So that upper row, we had to find which one was the smallest. And again, it's worth mentioning that every time we consider these computational costs, it's always the worst case cost. In this case, the worst case cost n would be that the last entry is always the one that has the shortest distance. And so that would be kind of the pathologically bad case, but that's the one that we measure our computational cost with. And then each of these processes, we have to identify the shortest path to each node. And so that means that we have to do that process n times for all of the other nodes in the network. And so this is the computational cost that I would expect us to be able to derive. If we know a little bit more about computer science data structures, in particular something called a heap, then that gives us a computational cost benefit of reducing n to log n, which is a little bit smaller. And so if you see the computational cost of Dijkstra reported, it's usually given in terms of n plus m log n, where n is the number of nodes and m is the number of edges.